I was telling my son about the problem and he asked me, why'd you put them next to the soup? I don't know. I just thought it would be funny. So, you should get 6 ways, but actually write them out so I can see that you got that. Now, if you take 6 is really 3 times 2. Write it that way. And then when you go to the 4 example, and if you want to try the 5 example, you'll be able to see it. If you can't see the pattern, don't sit there and spin your wheels. Text me and say, I did this, I got this, I'm not seeing the pattern yet. Can you help me out? It's like a 2-second answer to help you out. Once you get that pattern, then you're going to prove that that pattern actually works. That if I have N chairs and rotated them around, there's a certain way to place everybody in those chairs. All right, so we're going to actually go through how you prove something like that. And we're going to go back to the other day. I ended here. We go back to your notes, and I ended right here. This is the conjecture I want to prove. Dr. Sarandon and I, he's going to be coming to teach your class in the end of September, end of this month. Fabulous number theorist, just really, really strong number theorist. And we were talking about math induction and how, like, the typical way you show math induction, it just really doesn't equip you with when I'm going to use this. So I'm going to try to draw it out to you that usually it's examples. You start with examples. You kind of see like, hey, there's a pattern. I went over this last time. Like, there's a pattern that you go through and go, oh, it looks like the next thing is actually something to do with the previous thing. So you kind of have to see that. So if you got a problem from scratch that you've never seen before, you should always work examples right away. So you can get a feel for it, especially if it's some kind of argument like the one with the 3 chairs and rotating around. Work out examples on those things. So is anybody taking graph theory right now? Those are perfect places to start doing examples, like with small, if he says, Dr. Kovac, he's telling you, hey, I've got 10 people and they're doing blah, blah, blah. They're going to shake each other's hands or cross, whatever it is. Whatever the problem is, start out with 2 people, 3 people, and see if you can get a feel for why it's working. And then once you get that feel and say, hey, it looks like when I have 3 people, it has something to do with the 2 people case. Like I see that embedded in there. That's going to be the signal that it's good, probably induction.
And this is it. The step 7 just rewriting it. So you're rewriting the show.
Yeah, I did that last time.
Okay,
It's recorded.
Yeah.
Okay, so I'm now going to prove it. Okay, I went over this. I'm going to just do one more time going over this. The proof strategy is math induction. Because of 2 reasons. 1, I can prove it easily for small cases. And because I can see the previous case. So I don't want to scare you. I actually do want you to take real analysis. It's a great class. If you're thinking of going to grad school, that's like a big
thing. If you've taken real analysis, not just if you've taken real analysis, but you feel comfortable with it. Because like, you know, we have some of our captains have left and gone to graduate school, and I usually get the phone call back because I didn't have them in class. They call me back and say, my qualifying exams have analysis on them. I need help. But if you go with a little bit of strength behind you, you're not going to have that issue. OR programs. So one of our guys is in a stat program at Baylor. He has those kind of real analysis on his qualifiers. I could ask maybe pass them. But that just strengthens you and also broadens your choices of what you can take. A lot of our folks go get their graduate degrees and they're like thinking about what to take. And if they had a bad experience in foundations, they try to go to something that won't require anything pure in it. But then it makes you limited. Like you have less choices and you can't come back here and teach this course. I'd love you guys to come back here and teach this course in uniform. So and some of our faculty can. So it just makes you more resilient and strengthens you on your ability of teaching different things. We had a guy a number of years ago, don't laugh, his name is Brian Adams. He taught 476. Like it was very clear from day one, the day he stepped in here, he was going to be able to come and teach 476. That's the theoretical stats class that we have here. Not too many of those can come back and do that. You guys as a class should come back and teach here and be able to do that. Who's coming back? Nobody? Come back. Only Josh?
I really did only teach Ian 101.
No.
This
This is the most fun department, by the way. We always get called out by the dean and the soup. Like this is the fun place to be. So induction has steps. And you've seen it before because I saw it as in high school and I remember it from high school. You prove true for n equals 1. You should be long past that. If you did it right, you should have done n equals 1, n equals 2, n equals 3. I kind of see the pattern. Everybody can start a proof by working examples. So you should be long past that. So we already did this. We already did it for n equals 1, n equals 2, and I don't think we did n equals 1. We blew past n equals 1, but we did it for n equals 2 and 3, just on the board. So you guys did that already. So, but if you want to, the power sets, if I have s equals 2 thing or s equals 1 thing, then the power sets of S are empty set and singleton A1. There's nothing else. They got it. All right, tell me when I can move on. I quit coffee like a year ago, but today I had one, so I might even be more hyper than I usually am. All right, let me know. Good. Step 2, called the induction hypothesis. Assume statement is true for n equals k. The reason you do this is it's like you're doing the same thing every time. If I got to the third case, I'm using the second case to do the third case. So you're symbolically saying, I got all the way up to the kth case and it worked out. Can I get to the next step without actually having to just symbolically assume it? So you're just symbolically assuming that the previous step worked out. can I get to the next step? And that's what math induction is. So the previous step would be if I have S equals A1, A2, AK, then there's K elements, so the cardinality would be K. So this is your no. This is your nugget. Everybody got that? Okay. Step 3. Use step 2 to prove n equals K plus first case. So I'm going to do some bookkeeping for myself here and just label things. I'm just going to stay organized here for once. I'm going to call that SK so that it's the kth case. And I'm going to call SK plus 1. I'm just going to stick in one more element. And my no, I'm just going to reframe my no, is that the cardinality of the power sets of SK is equal to 2 to the K. I'm just going to rewrite it so like I have it all organized. It's let me see, I drew that messy. I've never drank something like that. I'd probably explode.
There's a like extra focus juice in it. It's better than it's
I think I had an 8-hour 255 one semester. They look like they're blown back every time you came in. Energy. 8 o'clock at night, it's the other way around. 9 o'clock in the morning is midday for me. That's what I feel like. You need this still, Isaac? Okay, so I know for the first K elements, like if I restructure this like this, SK plus 1 looks like it's a K. A1, AK, and then I got this AK plus 1. This is SK right here. Really, the question is, how many ways can I pair this new thing, this new element to the old ones? If you remember the feeling you got when you went to the board, that's what you were doing. You're just sticking in the next element. And I showed you, hey, you're getting your old subsets back, and then you're just pairing that old subset with a new thing. All your new stuff has got the new element involved. Do you remember when you went to boards, you kind of you did the 3 case and 4 case, and I didn't make you do something worse than that, but that's exactly what was happening. Well, you know that because you also did this little discovery assignment conjecturing the product rule.
It's still step 3.
Yes.
Okay.
So I just multiply them. That's what product rule says, right? If I made a tree, I'd have 2 to the k trees and 2 to the 1 branches on each one of the trees. Yeah, I'll put that in there. This is probably a good visual. Oops, what happened? Question?
I'm sorry, man, what is, N?
N is in the product rule, or product principle is what I called it in class. Remember when I had you take pairings of things and you made the trees the other day? You had
Yes.
N trees, M branches, made N times M. That's what you're doing. You're just taking this set and pairing it. You have already 2 to the K trees. And now you're gonna have 2 branches from each of those trees. So the total by product principle is gonna be 2 to the K times 2. So the N is the number of trees, the M is the number of branches. Yeah. Done.
By commutative high school math, I'm done. Isaac knows commutative is really important. That's why high school math works out so easy. Right? Laws of exponents. This is only true for the case where S is finite. If you remember at the beginning of the statement, it said S was finite. It's actually still true if it's infinite and countable, but we're gonna go there. We're actually gonna split that.
Countable just means that you can put a one-to-one map from whatever set you have to the natural numbers. That's all the definition is. But this thing still holds true. It means something different, but it still holds true if you have a countable set. And there's uncountable sets that don't have that correspondence, like the reals.
Okay, questions? So you'll be doing the exact same thing. Hard part, I think, is coming up with the formula that you want to verify, and then easy part is just running it through the machine. I mean, the induction part is just running it through the machine. It's a bunch of steps. Okay, questions? Of the induction process? Yes. You're supposed to do it for n equals 1, right? And if there's one element like that, then the power set the best. I can calculate it. It's empty set and it's singleton A1 is the only two things. So it holds true here.
Because 2.
2 to the 1 is the cardinality of the power sets, and 1 is the cardinality of S.
But you get the idea, like, the whole point of that first step is to get a feel with working an example, and no one should start with 1. You should do 1, 2, and 3 just to make sure they got it right. That's why I like to do it the way I did it with you guys, like on the homework, you have to come up with that formula, and the only way to come up with that is to play around with examples. Run some examples and see if you can come up with the formula.
So on the homework, can we do this? Are we supposed to do it for 1 or are we supposed to do it for 3?
I think I asked you. I put,
Because the first example is 3.
yes, and then I asked you to do it with 4.
Right. But then whenever we're writing this, like you
It's
start.
gonna be the same process. I'm gonna do, I did it for n equals. I did it, you don't have to do n equals 1, you can do n equals 3, right? So you did it for n equals 3, I did it for n equals 4, so that takes care of step 1,
Okay.
right? The point of step 1 is you make sure that you can see a few examples. At step 1, you're really supposed to even figure out if you're supposed to use induction. The worst thing in the world is when a cadet uses induction when they're not supposed to. I figure out if you're even supposed to use induction. And these steps that I gave you for running through the induction process, I don't give a crap about those steps, because if you can't actually take a proof and know I have to use induction here, then you can't use that tool for anything. It's just like someone who, look, I tell you, you can use the power rule or product rule or whatever rule, you know, integration by parts, I know how to do that. But I give you a random integral, and I don't know what to do here. Like, well, not really worthwhile to learn integration by parts if you don't know when to use it. The tool in your bag that you don't know when to use it is a useless tool. So in a real proofwriting class, like real analysis, nobody will tell you this is induction. You kind of have to play around. And there's more than one way to prove things. So something might work with induction and something might not. So I'm hoping Dr. Calkin will come to our class. I have to at first ask him, and then I'll give him the informed consent that it's 7:40 in the morning. So we'll see if he can actually do it. And then if he can come, he'll show you, like, there's multiple ways to prove one of these proofs that the rationals are countable. Okay, any other questions? Yes, if S is finite. So go back, and you're actually responsible for the in-class assignment. So go back and go re-watch the video. It should be clear. Oh, yeah, it should be around the power. What do you mean order? Order of a group, you mean? You don't have a group here. But if you think about order of a group, that is what it is. The order of a group is the number of elements in the group. It's cardinality. Right. Anything else? You feel ready for this next one? Okay. So on your fill in the blank, you might not have time to finish it all in here, but I'm going to have you catch up from your notes. You should be able to do 1 through 6.
So if you can't finish today, I'll give you time in class at the beginning of class Friday to finish it. I know Isabella's not gonna be here Friday. Anybody else missing Friday? All right, so you guys you have to do it on your own.